Hello students, before we start our chapter, I would like to request you all to watch our introductory 2 videos given by me so that you will be clear about the 3-step strategy to do DHAMAKA in physics exams. We have given the videos in the description box, or you can just click on our videos displayed at the end of this video for either introductory 2 videos or the next videos. Okay then, let's enjoy physics by Mr. Patel, who has a long, profound experience of 29 years of teaching physics in Sainik School, Balachadi.
So, how to minimize the power loss during the transmission from the power station which is situated at the remote place to the city areas where it is required for the users, that is for industries and the homes. To reduce the PC, these wires carry currents at a very high voltage V, and this is the reason for the high voltage danger sign on the transmission line. So, there are signs everywhere on the high voltage transmission line. When this power reaches the user's place, cities and villages, high voltage power is not safe. It will damage the electrical gadgets. For household and the industries, we need a current at low voltage, and hence at the other end the step down transformer is used, which lowers the voltage. It steps down means lowers the voltage, step up means higher the voltage. At the transmitting station, that is a generating station, it is step up transformer is used to step up the voltage, to increase the voltage, correct? Whereas at the other end, when it reaches to the city areas, the step down transformer lowers the voltage to a required use. Now next topic is cells, EMF and the internal resistance R of a cell. A simple device to maintain a steady current in an electric circuit is the electrolytic cell. A cell has 2 electrodes, one is positive electrode P and the another is negative electrode N. The positive electrode has a positive potential plus V, which is greater than 0 with respect to the electrolyte, that is solution, and the negative electrode has a negative potential, that is minus V, that is greater than 0 with respect to the electrolyte. Both the electrodes are deep in the solution, that is electrolyte solution. When there is no current, the electrolyte has the same potential throughout, so that the potential difference between the P and N is plus V minus V, that is plus V plus V, that is potential of the positive and the potential of the negative. This difference is called the electromotive force, EMF, and is denoted by E. Note that this E is not a force, it is the potential difference between the positive electrode and the negative electrode. Note that EMF E is the potential difference between the positive electrode P and the negative electrode N, and not the force. Consider a resistor R connected across the cell. A current I flows across the R from C to D, that is via P, C, D, N in the outer circuit outside the cell. Inside the electrolyte, the current flows from N to P. The electrolyte through which a current flows has a finite resistance R. The electrolyte has a resistance R because charges are flowing. The copper are positive charges and zincs are the negative charges. So, CuSO4 that dissociate into Cu and SO4 ions, Cu positive ions, they move from towards the Cu anode, and SO4 are negative, they move towards the negative electrode N. This is a Daniell cell having the electrolyte CuSO4, in which 2 electrodes, the copper rod and the zinc rod, this is the negative electrodes, they are deep, correct? Copper becomes positive and zinc becomes negative. The copper has positive potential, zinc has negative potential. When external resistance R is connected, when R is infinite, then V upon R is infinite, that is V upon infinite is equal to 0, where V is the potential difference between the P and the N. P and the N, when no current is through the R, the current is 0. And the potential difference between P and N is V is equal to E minus IR. IR is when charges flow inside the electrolyte, the current flows. Current flows inside the electrolyte is from N to P. Outside an external circuit, it flows from P to N via R, that is in R resistance. From the Ohm's law, V is equal to IR. The potential drop across R is equal to V, that is equal to potential difference between P and N. Also, if you connect, correct, that is equal to IR. So IR is equal to V, and that is equal to E minus IR. So IR you take on this side plus I small r is equal to EMF. Therefore I common into bracket capital R plus small r, and that is equal to EMF E. Therefore current I is equal to EMF E upon R plus R. Total resistance is R plus internal resistance R. So EMF E upon the resistance is equal to current in the circuit I. The maximum current that can be drawn from the cell is for R is equal to 0. If R is equal to 0, the maximum current, that is E upon R. The R is 0, then I maximum is equal to EMF E upon R. However, the most cells, the maximum allowed current is much lower than this to prevent the permanent damage to the cell. It damages the cell, so actual current is much lower than the maximum current IM. When a source of EMF E is connected to an external resistor R, the voltage drop across R, is V external, that is equal to IR according to Ohm's law, and I is equal to, we have already seen, the EMF E upon R, capital R plus small r, and that is into R, correct. Therefore I is equal to E upon R plus R, where R is the internal resistance of the source. Cells in series. Consider two cells in series. In a series combination, one terminal of two cells is joined together, leaving the other terminus of either cells free. Other terminals are of either cell made free, and one terminal is connected with the second one, correct. Suppose two cells of EMF E1 and E2, and internal resistance is R1 and R2 are connected in series between points A and C. Between point A, this is A point, this is C point. Let I be the current flowing through the series combination. I is current. Let VA, VB and VC be the potentials at point A, B and C. VA at the point potential at the point A, VB is the potential at point B, and VC is the potential at point C. Therefore, VAB is equal to VA minus VB, that is equal to E1 minus IR1, and VBC is equal to VB minus VC is equal to E2 minus IR2. Therefore, VAC is equal to VA minus VB plus VC minus VB, and that is equal to E1 plus E2, sum of these two, minus I into bracket R1 plus R2. Let E equivalent and the R equivalent be the equivalent potential and the resistance, internal resistance, then VAC is equal to E equivalent minus I into R equivalent. Equation number 2. Comparing equation 1 and 2, equation 1 and equation 2. The E equivalent is equal to E1 plus E2 and R equivalent is equal to R1 plus R2. If n cells are connected in series, then E equivalent is equal to E1 plus E2 plus E3 plus En, and R equivalent is equal to R1 plus R2 plus Rn. Now point to be remember, number 1, equivalent EMF in the series combination of n cell is equal to the sum of their individual EMFs. The equivalent internal resistance of a series combination of n cell is equal to the sum of their individual resistances. Number 3, the above expression is valid when the current leaves each cell from the positive terminal. However, if one cell of EMF E2 say turn into opposition to other cell, then the E equivalent is equal to E1 minus E2 plus E3 plus En. Say turn around in opposition to the other cells, then EMF equivalent EMF is equal to E1 minus E2 plus E3 plus En. Now cells in parallel. This is figure for the diagram for the cells connected in parallel. When positive terminals of all cells are connected to one common point B1, positive terminals of E1, positive terminals of E2 is connected to the common point B1, and negative terminals of both the cells are connected to a common point B2, and all negative terminals to another common point B2. the cells are said to be connected in parallel. Suppose two cells of EMF E1 and E2 and internal resistances R1 and R2 are connected in parallel between 2 points B1 and B2. Let I1 and I2 are the currents leaving the positive electrodes. The I1 and I2, they are current leaving from the positive electrodes. Right. At point B1, I1 and I2 flows in, whereas the current I flows out. At B1 point, the current I1 and I2, they flows in and I current leaves out. Since as much charge flows in as out, we have I is equal to I1 plus I2. So, current entering at B is equal to current leaving. No charge accumulation according to charge law of conservation of charge. As two cells are connected in parallel between the same 2 points B1 and B2, same 2 points, the potential difference V across both cells must be the same. Potential across between this B1 and B2 is the same for both. Say it is V. V across both cells must be the same. The potential difference between the terminals of the first cell, correct, is say V is equal to VB1 minus VB2, that is equal to E1 minus I1 R1. I1 is the current flowing from the E1 cell and R1 is the internal resistance of E1 cell. Similarly, the potential difference between the terminals of E2 cell is V is equal to VB1 minus VB2, that is the same for both, but the potential EMF of both the cells are different. So, E2 minus I2 R2. Now, I2 is equal to E2 minus V upon R1. Here from this equation I1 is equal to E1 minus V upon R1. Consider these two equations. So, I1 plus I2 is equal to I, that is I is equal to I1 plus I2, I1 is equal to E1 minus V upon R1 and I2 is equal to E2 minus V upon R2. Simplify it, therefore I is equal to E1 upon R1, this you take E2 this side E1 E2 and V on the right side. So, E1 upon R1 plus E2 upon R2 minus V common 1 upon R1 plus 1 upon R2. That is equal to E1 R2 plus E2 R2 upon R1 R2 minus V into bracket R1 plus R2 upon R1 R2. Therefore, V is equal to, now change the sides, correct, this whole V in this term you take left side and I you take on the right side. Therefore, V R2 plus R1 upon R1 R2, that is equal to E1 R2 plus E2 R2 R1 upon R1 plus R2 and I you take minus I. Therefore, V is equal to E1 R2 plus E2 R2 upon R1 R2 minus I. Now, take this term on the right side, that is R1 R2 upon the change, it will change, multiplication will be divided R1 R2 upon R1 plus R2. Therefore, V is equal to E1 R2 plus E2 R1 upon R1 plus R2 minus I into bracket R1 R2 upon R1 plus R2. If we replace the combination by single cell between B1 and B2 of EMF E equivalent and the internal resistance R equivalent, we have V equivalent is equal to E equivalent minus I R equivalent. So, E equivalent is equal to E1 R2 plus E2 R1 upon R1 plus R2 and R equivalent is equal to R1 R2 upon R1 plus R2. Again, the ratio of this E equivalent, EMF equivalent upon net resistance or equivalent resistance R equivalent is equal to E1 R2 plus E2 R1 upon R1 plus R2 upon R equivalent, that is R1 R2 upon R1 plus R2. This will be cancelled. So, E1 R2 upon plus E2 R1 upon R1 R2, that is equal to, again simplify, E1 upon R2 cancel, that is E1 upon R1, E equivalent upon R equivalent is equal to E1 upon R1 plus E2 upon R2, R1 cancel, so E2 upon R2 and R equivalent is equal to 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2, equation number 1. If negative terminal of the second is connected to the positive terminal of the first, then equation 1 this would still be valid with a E2 is equal to minus E2. If there are n cells of EMF E1, E2 and En and the internal resistance is R1, R2, Rn and R3 and Rn respectively connected in parallel, the combination is equivalent to a single cell of EMF E equivalent and internal resistance R equivalent, such that 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2 plus dash upon 1 upon Rn, and E equivalent upon R equivalent is equal to E1 upon R1 plus E2 upon R2 plus E dash 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 En upon Rn. Kirchhoff's rules. The first rule, called the junction rule also. This law is based on the law of conservation of charge. It states that at any junction, the sum of the currents entering the junction is equal to the sum of the currents leaving the junction. When currents are steady, there is no accumulation of charge at any junction. Thus, the total charge flowing in must be equal to the total current flowing out. Total charge or current. At the junction A in the figure, the current I3 enters, comes in, and there is arriving, and current I1 and I2 are leaving. So, I3 is equal to I1 plus I2. At junction A, the current leaving is I1 plus I2 and the current entering is I3. So, according to the junction rule, I3 is equal to I1 plus I2. I3 is equal to I1. Current entering is equal to current leaving. The second rule. This rule is based on the law of conservation of energy. This rule states that the algebraic sum of changes in the potential around any closed loop involving resistors and the cells is 0. The sign convention, we can take any direction clockwise or anti-clockwise. The potential, if it is from positive to negative, that is plus, negative to positive, correct, then it is minus. Consider the loops A, H, D, C, B, A. A, H, D, C, B, A. The sum of the changes of the potential around the closed loop we are taking in this direction, that is clockwise direction, is 0. Let us see, that is minus 30. The potential in the direction of the current, that is drops, is here potential more, here less, that is minus 30 I1 minus this 40 plus 1, that is 41 I3, this current is I3, and this is the battery potential from minus to negative to positive, that is negative to positive, that is plus, that is 45, and that is equal to 0. And for the second loop, A, H, D, E, F, G, A, H, D, E, F, G, A, this loop, whole loop, correct. This minus 30 into I1 current is flowing, plus 21 I2, this is in opposite direction, correct, 20 plus 1, 21, correct, minus 80, this is from positive to negative, that is V is minus, correct. Example 3.6, a battery of 10 watt and negligible internal resistance is connected across the diagonally opposite corners of a cubical network consisting of 12 resistors, each of resistance 1 ohm, each resistance of 1 ohm, correct. Determine the equivalent resistance of the network, and number 2, the current along each edge, correct. This is the network given, each resistance or 12 resistances, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all 12, each of 1 ohm, correct. The path A dash, AD and the AB are symmetrical. A dash, AD and AB, these are symmetrical, correct, the network. Thus, the current in each must be the same as I. The current in each must be same, that is say I current, in this branch also I current, and this all resistances are same, and the current divides into 3. Let us see, the total current is 3I. The I current flows along the AB, I current flows towards along the AD, and I current flows A dash. Here it divides into 2 parts, that A dash at D and at B. Here divides into 2 parts, that is say this is I2 current, I by 2, this is I by 2, here also I by 2, I by 2, here also I by 2, I by 2, and this. The same say I. At B, D and A dash, the current I splits equally. Thus, using Kirchhoff's first rule, currents in all 12 edges of the cube can be written in the form of I. Consider the closed loop A, B, C, C dash E, A. A, B, C, C dash E, A. Correct? This loop. According to Kirchhoff's loop rule, minus IR, correct, current in the current direction, the potential drops, that is minus R into I by 2 minus I into R, and this is potential from negative to the positive terminal, that is plus 10, correct. That is equal to 0. Therefore, EMF E is equal to the IR plus IR, this you take on this side, that will be plus. So, IR plus IR, 2 IR plus half IR, that is 2 and half IR, that is 5 by 2 IR. Say equation number 1. The equivalent resistance of the network, say it is R equivalent of the network, then R equivalent is equal to, the equivalent resistance is equal to, we know that from the Ohm's law, EMF upon potential difference upon current. The total current is 3 and potential difference is, that is, we have already calculated 5 upon 2 IR in the terms of this. The 5 upon 2 IR upon 3 I, that is equal to II cut 5 upon 6, 5 by 6 R. Now, R is 1 ohm. So, 5 upon 6 R is 5 upon 6, correct. Equivalent resistance is 5 upon 6 ohm. Now, EMF of the battery is 10 volt. The total current is 3 I, correct, and total resistance, equivalent resistance is 5 upon 6. The 3 I is equal to battery potential upon resistance, 10 volt upon 5 upon 6 ohm, that is equal to 12 ampere. So, total current is 12 ampere. It divides equally into 3 branches, that is along AA dash, AD and EB, that is 4A. I is equal to 4A. This is 4 ampere, this is 4 ampere, this is also in this branch 4 ampere. Here it splits into 2, that is here 2 ampere, correct, here 2 ampere, 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 correct, here 1 ampere, correct, because this combines I by 2 and I by 2, that is I. Here 4 amperes, here also 4 amperes, because I by 2 and I by 2, that total is current entering is equal to current leaving out of junction rule value.